Welcome back. Our next lesson is on transforming expressions. And we're going to think, essentially today's lesson is on thinking backwards from some of what we've been doing, especially with multiplying algebraic expressions. We're going to be kind of learning some of the foundations for factoring them, breaking them apart. Your prior knowledge today will be the primary properties of numbers we've studied in the past. So that would be the commutative, associative, and distributive properties. And you may forget especially these first two names, commutative and associative. Commutative, I'll often call it the any order property. And this is just the one that for adding and multiplying at least just means you can switch the order. Like 5 times 3 equals 3 times 5. And same for adding. But those don't work to reverse the order for like division and addition, right? Or sorry, division and subtraction. And then the associative property is the one where you can do like any group. So I'll often call that the any grouping property. Okay? So if I have 3 things I'm multiplying, I can multiply the first 2 and then the last, or the last 2 and then the first, or whatever, any of those groupings, right? And same with addition. And then distributive, we've talked about a lot recently, so you probably are okay with that. And then we're going to bring back greatest common factor, or GCF. So we're going to start with some warm-up. Our warm-up is going to be a little longer today just to get some more practice on things we've been doing recently. So first, multiplying out to expressions and then solving equations. Let's go ahead and have you do this warm-up on your own right now first. Then we'll come to the solutions, and then we have 2 more warm-up problems we're going to do afterwards. Okay, so I'm hoping you've paused and done all this workout yourself. Now, when you multiply this out, and you could use any method that we've learned or that you've learned to do this, you should end up with x squared plus 3x minus 11x. So that's going to give me minus 8x minus 33. Okay, so please check your answer on that. And then when you multiply this one out, you're going to get 2x squared plus 6x minus 20. Okay? So, let's go ahead and look at number 2. Now, if you noticed after you did number 1, I'm hoping you noticed that number 2 came from number 1. And so actually we can look back at number 1 to help us. Now, it's okay if you looked at number 2 and you're like, huh, wait a minute. You have seen a few equations like this in the past, but I want to remind you of something. We can use a really important property we learned recently called the zero product property, but only if something's in factored form. And you notice that 2 is not in factored form for A or B. But the good thing is we saw back here what the factored form was. In this case, x plus 3 times x minus 11 equals 0. So I want you to realize that because this expression is equivalent to that expression, the 2 equations are also identical equations to each other. And now we can look at this and say, oh, I know what the solutions are. So if you didn't know how to do that and you want to go ahead and pause and finish it again yourself, go ahead and do so. But let's solve this, let's finish this one out. We can see the 2 solutions for this are either negative 3 or positive 11. Because remember, that's what you plug in here to make the whole thing equal 0. Let's check the next one. And again, we know that this one can be put in factored form, and that's the way to solve ones like this, okay, if it's squared. So this one is 2x plus 4 times, minus 4 times x plus 5 equals 0. And I guess we can see this one easily, the solution. This one maybe might be a little tough for you to see, but remember we can just do 2x minus 4 equals 0, and then we get 2x equals 4, and x equals 2 in this case, right? So we have x equals 2 or x equals negative 5 are the 2 solutions from that one, and then we're done with those. Let's go ahead and look at our next 2 warm-up problems. So here are our last 2 warm-up problems. Again, go ahead and tackle these on your own, please. And if you're still a little bit rusty on GCF or something, that's fine. If you want to go ahead and unpause and look at the solution with me together on that, that'd be fine. So go ahead and pause it right now. Okay, so I'm assuming you've gone through and looked at that. Let's go ahead and do these together. So number 3, show the following are equivalent to 2x squared plus 6x minus 20. You probably recognize that from our other warm-ups that we just did. So I'm just recycling this one because we can see that it shows many ways, right? So this goes back to that form implies function rule. There's all these different ways that this same expression or function can show its face. Well, for part A, pretty much the best way to actually show this is to realize that we can distribute this 2x into both terms here. So we can see that this becomes 2x squared plus 2x times 3 is 6x minus 20. And that's equivalent to the original thing already, so we're good to go. Part B now, you might look at it and be like, well, what do I do for this? How do I show this? I want to remind you that this goes to this commutative property I reminded you guys of, where the order of the addition doesn't really matter. And you might think, wait, but there's subtraction here, and you said that you can't do subtraction. Well, remember, technically, in the original one, minus 20 is technically plus negative 20. So we can, as long as we keep that as negative 20, that guy can be switched around with the other terms as well. So you can see here, negative 20 plus 2x squared plus 6x is just the addition being rearranged. So really, we can just say that it's 2x squared plus 6x minus 20, and that's just because how numbers behave by this commutative property. The next one involves another thing that we've had to do, which is combining like terms. So hopefully you identified that. We can see that 5x squared minus 3x squared, and then the plus 6x looks like it's already the same, and then plus 7 minus 27. And at that point, these like terms result in 2x squared, and then we have our plus 6x, and then 7 minus 27 is going to be minus 20. And then finally, I'm hoping you recognize this as we've learned before with factoring actually. There's two ways you could go about D here. You could distribute the 2x through here, and then this negative 4, and be careful and make sure you remember that that's negative, into here, and then combine like terms, kind of like we did like in part C. Or you could also recognize that they both share that x plus 5, and so I can actually write 2x minus 4, and I can pull that x plus 5 out as a common term to both of those things, like we've learned. And since we've already actually done this in our warm-up number 1, we actually expanded that, and we can see that that's equal to, because we already did that work, 2x squared plus 6x minus 20. Okay? So again, there's two ways. You could have also distributed that and this, and then combined the like terms. Now let's get to number 4. I don't quite have all the space in the world to do this, so we'll write the answers here in a moment, and I'll write the work right here, and then we'll get back to it. So number 4, find the GCF. Remember, greatest common factor, it says exactly what it means. It's the largest number that's in common as a factor, right? Greatest common factor. So if I wanted the GCF, and actually we'll often put it in parentheses almost like a function, because GCF itself is a function with actually 2 inputs. So you have 2 inputs and 1 output. So we could write GCF parentheses 12, comma 8, and that just means find the GCF of 12 and 8. It's not really a coordinate pair necessarily. And there's a way that we've looked at this before, is if you actually break the number into its complete product of primes, in this case 12 is going to be 2 times 2 times 3 if we completely break it down. And the same for 8, but it's 2 times 2 times 2. Well, all we have to do is identify as many factors that are shared by both things. So this they both have a 2, but they both have another 2. Now this is not uncommon and there's nothing else. So it turns out the GCF of 12 and 8 is going to be 2 times 2, which is 4. Now you may have just done that in your head, but the method's important for the next one especially. You may have just said, oh yeah, I know 4 is the largest number that divides into 12 and 8. But just to remember that, I want you to think about how we do this. So let's actually tackle the next one real quick. Actually, I'll do that down below here. GCF, and I said 36, 234. So same thing, and if you needed the reminder here on how to do it, why don't you go ahead and pause and do this one on your own, just to make sure you have, you know how to do it, okay? But let's do this together. 36 is equal to 2 times 18, right? And that's going to be 2 times 2. Oh yeah, and it's also 9 times 4. So here's 4, and then we're going to need a 9, which is 3 times 3. There's lots of ways you could break it down. You could have broken down into a factor tree if you remember that. That would be helpful as well. Then you could see 2 times 2 times 3 times 3, right? But either way, you can see it's 2 squared times 3 squared, and then 234. I like to divide by 2's if I can, and I think this one's divisible by 2. 200 divided by 2 is 100, and then 34 is 17. So this becomes 2 times 117. Now this is where it gets a little bit tricky. You can use a calculator, no problem. I'll just tell you this one's divisible by 3. And I'm thinking of 117 as 90 plus 27, just so you know. And those are easy to see divisible by 3, even though 117 is not really so easy. Divide by 3 and we get 30. Divide by 3 and we get 9. So we can actually see this is going to be 2 times 3 times 39. So 117 is 3 times 39. And we're almost done. 2 times 3, and 39 is 3 times 13. And let's see what is in common here. This one's got a 2, and so does that one. Is there another 2 here? Nope, so that's not. There's a 3 here and a 3 here, and I don't think that I see anything else. So it seems to me like the greatest common factor. Oh, wait a minute. No, I missed one. You might have been calling out my name while I was saying that. There's another 3. So actually there's a 2 and 2 3s. And I was thinking in my head that was wrong because I knew what the answer was. So our final GCF is going to be 2 times 3 times 3, which is 18. So we'll write that down here. Okay. Our main part of the lesson really isn't super long today, so we'll just dive into a few examples there, and then we'll be done for today. Okay, our actual lesson here really only has 2 examples. It's kind of just putting together a lot of the stuff we've been doing the last few lessons, to be honest with you. We did a lot of great prep in our warm-ups, and let's go ahead and jump into this. The main thing here really focuses on the GCF and using it to help us identify what we can factor out of an expression. Okay, so that's a really important concept here. So I put that here. The GCF tells us what we can factor out of an expression. So if we have an expression with multiple terms in it, if each term shares a certain thing, I guess it's hard to, how do I say this? The GCF of each of those terms is what can be undistributed out of there. And that's kind of what we're thinking. And it's very helpful for solving equations with the ZPP. So what we're going to do is we're going to look at one together here. Then I'll ask you to pause and do the other one on your own. And we'll do the same thing for number 2. We'll talk a little bit about it, but then I'll have you finish doing that on your own. So number 1, for now the equations we're going to solve are going to be basic ones like these. So they're not super complicated. We've actually done a couple like this. But let's think about this in terms of GCF. It's going to be helpful to think about breaking this down. Well, 9x cubed is 3 times 3 and then times x times x times x, and then 15x squared is 3 times 5, and then that just has 2 x's, right? So if we want to identify the GCF here, they both have a 3 and they both have 2 x's, so 3x squared. Now, many of you are probably just okay looking at this. You don't need to write all your steps out necessarily. If you can notice, okay, 9 and 15, what's the highest thing in common? 3. And then x cubed and x squared, well, what's the most amount of x's that both contain, right? The highest number of factors. And you can see there's 2 of them here and 3 here. So we could at most pull 2 of those out of everything, right? So what our final answer here is going to be, we can take a 3 and an x squared and undistribute it, right? And you can look back here, what's remaining? If I took a 3x squared, oh, there's a 3x, right? And you can always check your work by working backwards and distributing it back in. And the 15x squared leaves me with just a 5 there, right? Now, if I solve this, notice, this is like when we've done before, this is 3 times x squared. What's an easy number to tell that makes everything 0 based on this factor? Just 0, right? So here we can see x equals 0. And then from this one, it's a little tricky. 3x plus 5 equals 0. but if you subtract 5 and divide by 3, we can see that negative 5 over 3. You could also say 1 2/3 negative, or however you want to put it. But I'll leave it as negative 5 over 3, and there's our two solutions. So again, why don't you go ahead and pause and solve part B, and then we'll dive into number 2. Okay, let's check our work here. So again, if you want to identify the common factor, what's in common between 8 and 14? It looks like it's just a 2. So even though I could break that 4 down more, I'm just going to leave that one. So this becomes, and then 14p, there's just one single p, right? So we can see the GCF here is just going to be a 2p for this one. So we'll write this as 2p times, well, what's left in here after I factor out the 2p? Well, if I divide a 2 out of this, I'm left with 4, and then there's still one more p in there, and then minus 7, I believe, right? And remember, this helps us identify what's remaining when I do this, equals 0, and same deal here, p equals 0, and then if 4p minus 7 equals 0, we add 7 and divide by 4, and we can see that it's 7/4. And again, you could write 7/4 in many ways, but I just leave it as a fraction. That's the easiest way to write it right now. So number 2, write each expression as the product of 2 expressions, if possible. Now when it says if possible, what we're really saying is if the GCF is not just 1, right? Any 2 numbers that are co-prime, if you remember that term, mean that they don't have a common factor except 1. And so let's take a look and see. In fact, you might start by looking at this and identifying, are there any of these that you can see don't have a common factor, meaning they're already factored or as much as it gets? You can take a look at that and see right now. I think I noticed that this one doesn't have anything in common. So the actual furthest factored out it is just himself. That's it. Okay? The other one I notice, if there's another one, well, actually I think that's the only one that doesn't actually factor any further. You might be looking at A, because you'll notice this has a squared and b squared, and the variables are different, but the 15 and 21 at least has something in it. So let's start with that. This is gonna, looks like 15 and 21, the highest number in common is 3. So if I break a 3 out, I'm left with 5a squared plus 7b squared. And now I honestly think that's about as far as I can go with that one. Go ahead and try B, and honestly try B, D, and E on your own real quick. And you can pause it, and then we'll check it together. All right, let's look. I think you can notice that there's an A in common to both of these terms here, so we can get A times B minus C. And then let's take a look at this one a little bit longer. We want to get used to being able to maybe do this in our heads a little bit here. Let's first look at the x's here, okay? What's the highest number of x's that all of the terms share? This has 3 factors of x, this has 2, and this has 7. All of them have, at most, 2 factors, right? Because this one has 2, so you pretty much need to look at the lowest exponent, right? So what we can do is we can say, okay, well I can take x squared out of there. Well, what's the lowest exponent of y here? There's 4 factors of y, 5, and then just 1 here. So it looks like you can take one single y. So what's left? X times y to the 3rd for that one, plus, well, I pulled all the x squareds out, so I'm just left with y, and I only pulled one y out, so I'm left with y to the 4th. And then minus, I took 2 of them out, so I'm left with 5 factors of x there, and I actually took that entire y out. So it looks like that's about as factored as that one gets. And then I threw E in here on purpose just to make sure that we are still getting the hang of ones that look like this, okay? I want you to remember that x minus 4 is the GCF, now that we're thinking in terms of GCF, for this whole term. Don't forget, this can be thought of as a whole term, and this whole term, right? And so, however you want to look at it, we've typically kept the x minus 4 at the end, but it doesn't really matter. X minus 4 can be the thing that we pull out, But then what's left when we pull that out? Well, there's a 5x and a plus 13 that's left. Okay? So that's pretty much everything that we're going to talk about with our lesson today on transforming expressions. What we did was we reminded ourselves of the different properties of numbers, and they also extend to algebra that we've learned. We've reviewed what the greatest common factor is, and we've used that to help us break apart or factor expressions, and even help us solve some basic equations using the zero product property. See you next time.